Welcome to Quantum Curious, and in today's video, I'm going to discuss an important paper that came into being in scientific community in 2017 and was published in Physical Review A. So I haven't made a video for a while on quantum optics, quantum cryptography, and related to some review papers or different papers in general. So you can say today is the revival of the video lectures and video series. So today's paper's title is Passive State Preparation in Gaussian-modulated coherent state quantum key distribution, and uh, it was uh, written by Pinkai and Philip G. Evans and Warren Ice and Paul, and all of the authors uh, will, uh, are related to the universities in USA. So we know that Gaussian modulated coherent state quantum key distribution, in which we use coherent states and we modulate it using Gaussian modulation, meaning we encode the information in the quadratures of the electromagnetic field, that is the coherent states, and the quadratures are Gaussian distributed, and they follow the Gaussian distribution with uh, with some precise, or you can say fixed variance. So we know that Gaussian modulated coherent state QKD. But what is passive state preparation? So in the in the early days of the quantum cryptography, we know that we only used the discrete variable of state of light or state of or electromagnetic field, and we were usually encoding the information in polarization state, like the states used in uh, protocols, the famous protocols like BB84. But then uh, the idea was introduced to encode the information in quadratures of the electromagnetic field, and this idea came into being in early 2000s. So the continuous variable, that is in short form CV-QKD, is famous because it is compatible with the present age telecommunication devices, and we have to implement uh, this QKD using just simple optical devices like beam splitters, modulators, and some coherent uh, measurement devices like homodyne and heterodyne detection. So it is very easy to implement and compatible with the present age telecommunication devices. So there was an issue that we can not modulate perfectly the coherent states because our modulators or modulating devices are not that much perfect. So there is some kind of errors in modulators, and this can increase the vulnerability of our key, and it can uh, increase or open some loopholes in our security of the overall quantum cryptographic setup. And also, it was not that much a efficient way to modulate the coherent state in a setting where we need a high transmission rate. So in the setting where high transmission rate is required, the modulators does not or cannot modulate the coherent state in that much speed that is demanded uh, on the setup, and that's how uh, they are not that much efficient in uh, quantum key distribution setup. So these was the precisely two main reasons in order to uh, you can say introduce this passive state preparation. So this passive state preparation idea was first introduced in uh, discrete variable quantum key distribution. And it was used in some kind of decoy state quantum key distribution because we need very high transmission due to very high transmission demand, and that's why the passive state preparation idea came into being first and was firstly introduced in discrete variable QKD. So this is the, I think, the first instance in which this passive state preparation scheme has been introduced in the continuous variable quantum key distribution, and in precisely the Gaussian modulated coherent state quantum key distribution. So let's see what this scheme is about. So we know that the Gaussian modulated coherent state, the whole ensemble of them can be seen as a thermal state, because from the point of view of Bob and E and an adversary, they are just the thermal state, because the ensemble of Gaussian modulated coherent state can be approximated on as a thermal state. So the authors in this paper is saying that rather than using Gaussian modulated coherent state, why not use the thermal state uh, as a whole, as a quantum state, in order to distribute the key between Alice and Bob. So this setup, or this usage of thermal source, can simplify the whole setup of a key distribution uh, in this continuous variable regime. So, as we know that in the Gaussian modulated coherent state, thermal states are the states that Eve and Bob is looking at. So rather than using thermal, or rather than using Gaussian modulated coherent state, Alice can use the thermal source. And the security and analysis will be same as the Gaussian modulated coherent state, because there is no difference between the point of view of Bob and Eve. Uh, they are uh, viewing this incoming state as the thermal state in both the cases. Rather, if we use whether we use Gaussian modulated coherent state or using thermal state. So Alice here is using a thermal source in order to distribute the key between her and the Bob. So the initial quadrature components, or uh, the two quadratures of electromagnetic field are X in and P in, and they are input quadratures of the thermal source. And Alice uses here the balanced beam splitter in order to produce the two spatially, you can say, separated mode, that is the mode 2 and mode 1. And mode 2 Alice uses for her estimation of the outgoing quadrature, and she is employing here the conjugate homodyne detection. And on the Bob side, she's transferring the mode 1, that is another, you can say, the spatially separated mode of the incoming quadrature of or incoming thermal state. And here we have a vacuum state uh, in this, you can say, in this input port of the beam splitter point. So mode 2 and mode 1 are kind of entangled because of the beam splitter operation. So we know that beam splitter operation is a passive operation in phase space setting. So it is not it is just distributing uh, the photon numbers or photon states in the two modes. and the photon number will remain same. So there is no addition of energy uh, or you can say withdrawal of energy. So the two modes are going to be the same with conserved photon number, but they are distributed in two separate modes. So the first task of Alice and Bob will be to approximate their estimation and the error in estimation. So Alice first is going to approximate the outgoing mode by applying a local homodyne or conjugate homodyne detection by detecting the quadrature of mode 2, and the values are x2 and p2. So Alice is going to uh, estimate the outgoing mode x1 and p1 by employing as I have said earlier, the conjugate homodyne detection. And Bob on the other side also is also going to employ another homodyne detection, that is the conjugate homodyne detection, to estimate the incoming quadratures values. So in this paper, the author is just saying about the x quadrature and p quadrature can be estimated in the similar way. So there is a symmetry between x quadrature and p quadrature because both are measured with the same precision. So working out the noise or the error in estimation of the x1 and x2 quadrature uh, will work for both the quadrature, that is for the conjugate p quadrature. So first, the author is showing that what Bob will got, but what Bob will get after measuring the incoming quadrature. So x1 is the incoming quadrature, and where we have xv1, that is the vacuum mode introduced during the conjugate homodyne detection, because we have the same setup on the other side, uh, on the Bob side. So we are employing another beam splitter. So this splitter is also going to input another vacuum mode. So this vacuum mode will be going to uh, will be going to appear in that quadrature values. So Alice's measurement is shown by this x2 value, and Alice is going to estimate the outgoing mode with this expression. So the overall uncertainty of Alice's measurement is going to be quantized with variance. So we know that how much variance or how much uncertainty in Alice's measurement about the Bob's quadrature. So this uh, uncertainty will be going to add as another trusted noise in this overall security analysis that we will or that the author has mentioned here. So in order to uh, uh, eliminate the vacuum noise or the short noise, we have to eliminate the variance of that vacuum noise. So here the Alice is calculating the state preparation noise, as she is eliminating the vacuum noise from the uncertainty in her measurement and in the Bob's measurement. So this epsilon A is a state preparation noise, and it is going to be a trusted noise in the overall security models. So we have overall, you can say, But author is mentioning that we can control in noise in a practical setting because we know that variance is related to the average photon number, and we if we put that expression in that noise expression, we are going to have relation with state preparation noise and the variance that else is using, or the variance of the thermal uh, state, or the temperature values of the thermal state. So in order to minimize that variance or that uncertainty in Alsace and Bob's measurement, we have to optimize that VA. And we can optimize it by using an optimal number of average photon number and controlling that attenuation. So by the combination of attenuation and average photon number, we are going to have a variance, or you can say an optimal variance that is going to control or minimize that noise. And that's how we can increase our secret key rate. That is the security parameter. And if we can increase the secret key rate, we can make the performance of this scheme comparable to the scheme where we have actively modulated the Gaussian or actively modulated the coherent state with the Gaussian distributed uh, variables. So that's the whole scheme, and that is the main concept behind that uh, state preparation scheme that is introduced in this paper. So next is the section of simulation results. So we know that the secret keyword is just the subtraction of the mutual information, that is the uh, common information between Alice and Bob's measurement, and the high level bound, that is the maximum classical information that Eve can imply, or that Eve can gain after employing an optimal attack on the Gaussian channel. So it has been shown that the optimal attack the Eve can employ on the Gaussian channel should be a Gaussian attack. And in this setting, the author is uh, calculating the asymptotic Q rate and supposing and assuming that Eve can employ the most powerful attack in that setting is collective attack. So we know that there are three kind of attacks that Eve can employ. That is the individual attack, uh, collective attack, and coherent attack. And we know that the most powerful and most general attack is coherent attack. But for the case of simplicity, we can assume that Eve is implying a collective attack, and after some finite key analysis, we can use some tools like entropy accumulation theorem or Gaussian definite theorem, and we can raise the overall analysis to the general attack. So for the case here, we can uh, still assume that the Eve is implying collective attack, and it can give us the lower bound on the secret key rate. So the transmission is assumed to be a transmission of a fiber optic channel, and it has constant attenuation. And we have the, you can say, the noise introduced by the Bob's measurement on his side, and it is the noise produced by the overall setup, that is the heterodyne detection setup, and this noise is also Gaussian. And the channel noise consists of the channel losses and the untrusted noise. So in this case, the excess noise is going to be the addition of the state preparation noise and noise from some untrusted sources. So we know that attenuation or state preparation noise can be minimized by using some optimal parameters like attenuation and average photon number of thermal state. But this noise, that is the noise from some untrusted source, is going to be fixed. And it is usually assumed to be 0.01 of in short noise units, and it is optimal for experimental setting. So the total noise is going to be the addition of the channel noise and the device noise. So the overall mutual information can be calculated using the variance of the Alice and Bob and some conditional variance. And where here V is equal to the short noise and that is the inherent noise the uh, in the you can say the experimental setup, and VA is the uh, variance that is related to the attenuation that is Alice is applying on the outgoing mode 1 and the average photon number of the thermal state she is using. And we can calculate the Halever bound using some covariance matrices. So we have covariance matrices AB and covariance matrices of Bob condition on her on his measurement, and we will see these detail in the upcoming lectures because the author has not mentioned the overall analysis because that has been done before that, and and he is just mentioning the or he just mentioned referencing that source with reference 30. So we can see that how it can be calculated, but it's not that a big deal. It is just calculating some covariance matrices, and because we know that the overall uh, Gaussian states uh, can be completely described by the first moment and the second moment, and we can extract the entropic information from this, and we can calculate the high-level bound uh, that the Eve's maximum information she is attaining by employing a collective attack. So here we can calculate the Eve's high-level bound by symplectic eigenvalues, and the overall performance of the simulation result is shown in this plot. So we have secret key rate on the y-axis and distance on the x-axis. So as the distance is increasing, the losses will be going to increase, and also the attenuation imposed by the quantum channel, that is the fiber optic channel, is also going to be increased. So for the average photon number 50, we are going to have a transmission distance of about 40 kilometers. And for 100 photon number, we are going to have a transmission distance, that is the distance on which we have a positive secret keyword, meaning we have mutual information more than the high level information. So we can guarantee that our protocol of secret key distribution is saved. And for 100 photon number or average photon number, we have transmission distance about 120, and for 500 photon number we have transmission distance that is above 150. So the optimal uh, average photon number that we have to use for the input thermal state is 500 in order to get the optimal performance from this protocol. So after that, author is mentioning how we can we can check the quality of the source by doing some quantum tomography, and he is using uh, the second order correlation function in order to do that, and plotting the value of x and p, that is the variance of p and x. And we could say that this is the whole plot of thermal state in phase space. And here, the small circle orange is showing the plot of vacuum state. So in order to check the quality of our thermal soul, we have to do that quantum tomography, and it will be done on the LTIS side of laboratory in order to guarantee that that the state that we are using is the thermal state. So in the in the discussion section, author is mentioning some limitation of the analysis that he have discussed above. He's saying that uh, uh, the use of the multi-mode thermal state should be used with a precaution, because if the multi-modes are entangled with each other, Eve can, or any adversary can use that entanglement for his own advantage, as she could measure the quadrature of some mode that is not going to uh, be measured by Bob, and she could store the information without being detected. And these kind of assumptions should be taken in the upcoming or for the future work for the passive state preparation scheme. And another question, he has mentioned that the randomness is generated from a thermal source. So can we trust it? Uh, as has been discussed, while quantum randomness is ultimately connected to quantum superposition states, in the trusted device scenario, thus the state received by the detectors does not need to be a pure state. For example, trusted randomness can be generated by measuring only one photon from an entangled photon pair. Even if cannot access the other photon. In our scheme, photons from the thermal source are generated from through spontaneous emission process and are entangled with the atoms inside the source. Given the source itself is protected from Eve, true randomness can be generated. So it is answering the question that can we trust this randomness, because uh, the photons in the thermal states can be captured by Eve, and the overall randomness could be in not be trusted. So this is answered by the argument that the thermal source is going to be in a trusted laboratory, that is the ALSIS laboratory. So there is no uh, question on the guarantee or the untrustedness of the randomness. So this is the whole process of these passive state preparation schemes, and I hopefully you have understood all the process and the scheme that has been mentioned uh, or introduced in this paper, and that is for all today. Bye bye.